afternoon. Can you hear me? Okay. Hey, you know it's my birthday. Happy birthday! And I think on your birthday you get to play your favorite song. That's it. The Animals from Newcastle. My birthday year, therefore. This number. Approximately. I think it's the best song ever. Okay, hey, you should, if at all possible, keep open March 24 at 11 in the morning. It looks like we'll have a Nobel Prize winner in cell biology, and actually in medicine and physiology. We will come to see you and we'll give a talk in the Laurie Student Big Theater. And I think we're going to give you some extra credit somehow if you go there. So also because it's my birthday, you give presents. Now, there will be some twist to this. It's not free, not to show up and you get it. That's not the way it will work. So we'll get to that. But I think I'm almost certain it's 11 a.m. I'm very certain of the day. I'm also pretty certain of the place. So details to follow. Alright. So we're going to try to understand why it takes the 2 sodium to move the glucose into the epithelial cell over the apical membrane. And let's also try to understand why the membrane potential is what it is in mammalian cells. And for this type of understanding, we need to think of the membrane potential and the concentration gradient together, and they form what we call the electrochemical gradient. And we need to understand that there's energy stored in concentration gradients, and there's energy stored in membrane potentials, and we can compare these amounts of energy. And we can see this in this simple equation, which tells us here that the delta G, that's the free energy change of a total reaction where a charged molecule moves over a membrane, and that's change in free energy, which comes in the units of kilocalories per mole, that can be calculated from the change in response to the membrane potential, the delta G volt, and the change in response to a concentration difference, the delta G concentration. So that's simple. So we need to remember that reactions with a negative delta G are the favored reactions. So if we think about sodium moving into a mammalian cell, we know that sodium ion is moving down concentration, that's favored. And we know it's moving with the membrane potential because it's negative in, positive out. The positive sodium ion wants to move into the cell, or the mammalian cell membrane. So we're going to get a big negative delta G for the movement of sodium into a mammalian cell. That's because there's a delta G component for the membrane potential and for the concentration, both favor the movement of ion. Okay. Now, what we see here essentially is that some form of energy can be converted into other forms of energy, or different forms of energy can be compared to each other. And I've written a couple of pages about energy and what it means in biology. I've posted that on the web, and I invite you to look that up. And I'll make sure that you know where the link is. Okay, so if we can see that there's a change in free energy when there's a movement of an ion, and there's a membrane potential component and a concentration component, and what are those two? So there's some physical chemistry, and it just tells us that for the membrane potential component, the free energy change is the same as this formula. Formulas in blue are not going to work. So it's the same as this formula. So Z here is the number of charges. F is the Faraday constant. Faraday was one of those physicists from Cambridge, England. And he came up with, I guess, or people came up with the Faraday constant. And it simply converts potentials to energy. So if we have a certain membrane potential, then we multiply with the Faraday constant and the number of charges that we are moving. So for sodium, the number of charges, Z, or Z, if you're British, equals 1. Or Z American. You say Z or Z? Good. And I think the British say Z. Not sure. I'm not British. So for sodium, Z is 1. For protons, Z is 1. But if we're talking about calcium, then we have 2 plus, and Z equals 2. So if we move more charge, then there's more energy involved. Okay, so we can calculate that. Now, what about if there's a concentration difference? Then physical chemistry gives us this formula that you don't have to learn. But maybe it's interesting to look at it. What we see here, the change in free energy is proportional to this number here, negative 2.3 times R. R is the gas constant. It's something that's used to convert concentration ratios to energy levels at a given temperature. Now the temperature is in there as well. And then here we have the concentration ratio, but we take the log of that. And you can imagine if we have two concentrations and they are the same, and that ratio equals 1. And the ratio, if the ratio is 1, then we take the log of that, then what do you get? Nada. So if the concentrations are the same, then there's no energy stored in that concentration ratio. So by taking the log, we're essentially taking a measure of how far away we are from equality for the two concentrations that we're taking the ratio of. So we're taking really the order of magnitude by which we are away from the point where the concentrations are equal. Okay, now that's not also important. What is kind of nice is that if we take for the temperature 300 Kelvin, which happens to be 27 degrees Celsius, and that is roughly 78 Fahrenheit, I'm going to guess, close by. And more important, that's the temperature that we can often find at a nice place like the islands of Hawaii. So in a place like that, we have a nice 300 Kelvin, and this becomes a rounded number, or you can round this to negative 1.4. Negative 1.4 kilocalories per mole is a number that will come back. So negative 1.4 kilocalories per mole times the log of a concentration ratio, that gives us an estimate for how much energy there is involved in the movement of a molecule over a membrane in response to a concentration difference. So let's just look at some examples and make this work. If you want to read more, you can also read in the book. So let's just say we have a concentration difference. So we'll just look at that first. So let's say here we have a cell, and it's surrounded by a membrane. Inside the cell we have 0.01 molar of glucose. That's the concentration. Outside we have 0.1 molar of glucose. So if we have a channel or a uniporter for glucose available, is it favored for glucose to move in? Yes, it is, because that's downgrading. Okay? Then how much energy would be released if this glucose moves in? So then we use the equation that we just had, and it simplifies here. If we think that we're in Hawaii, which from now on we will mentally always be. So we're in a happy place in this class, and a nice temperature, which just makes that the numbers are easy. Okay. So we had a tenfold more outside than inside. And what I like to tell you is really I take the concentration ratio, where I take the ratio of the concentration at the point where we start our origin over intended. So I take O over I. Correct? Yeah, that's correct. That's what I want to do. So then what we see is that the ratio here is 0.1 over 0.01. That's actually the figure 10, the number 10. And the log of the number 10 is 1. So that means we have a negative 1.4 kilocalorie per mole released. However, if we move only 1 mole of, if we move 1 mole of glucose, then that's negative 1.4 kilocalorie per mole, which is released. There's an assumption that we make in this type of calculation, and the assumption is, essentially this is a cell of infinite size. In other words, if we move some glucose in, we don't change the concentration of glucose there. We can change that assumption with the same consequence, and we can say that the effective concentrations on both sides of the membrane are not affected by the molecule that moves. And this is a good assumption usually for cells, because usually we just have a supply of a nutrient, and within the cell that nutrient is consumed and is being kept at a stable concentration. So effectively we assume the concentration stays constant. Another way to say this is we're calculating the energy for the first molecule that moves across. We express it as the energy change per mole of molecule. Alright, so that's that. We can do that. So now let's see how much energy is stored in the membrane potential. Let's just take a cell, and we have sodium that might be moving across the membrane here. And let's just say it moves in. But to make it simple, I've put the concentrations equal inside and outside, just to take the effective concentration out. So now we're looking at the effect of membrane potential only for the movement of sodium. So we assume now there's an open channel and sodium can move in. So what is the free energy change? Well, the free energy change, there it is. It's given by this equation, Z equals 1. So we fill in the numbers, and what we get here is negative 2.3 calories for 1 millimolar. For 1 millimolar, if it moves, I should say. So it is actually negative 2.3 kilocalories per mole. But if I change the question and I say we're only moving 1 millimole in total, I should have said 1 millimole here, not 1 millimolar, then it's negative 2.3 calories. Okay, so negative 2.3 kilocalories per mole. How do you do this? Now the good thing is you probably never have to do this. If you look at this at home, and you should, you will easily follow and understand. Okay, so I've put the units here underneath, that's also convenient. Okay. So now in a complete electrochemical gradient, let's take a somewhat realistic situation, something that represents perhaps a neuron or any mammalian cell. And we can, we can assume we're going to be pretty close to typically 150 millimolar of sodium chloride outside of the cells and 15 millimolar of sodium chloride within the cells. Pretty close to that is what we will be. It's not exactly like that, but it's close. So it's an approximate 10-fold concentration ratio. By the way, the 150 millimolar of sodium, if you've ever been in the hospital and needed an IV, that's what's in the IV. 150 millimolar of sodium chloride. That's what's in it. Why is that in it? Because that's isotonic with what's in your blood, in the fluids that surround your cells. Okay, so these are close to real life values. And then we can assume a membrane potential, enough said of 75 millivolts is pretty close. think anywhere between 70 and 90 millivolts is a realistic value for mammalian plasma membranes. And it is positive out, negative in. Okay, so now we're going to say there's a channel and sodium moves in. So what is the delta G for that movement of sodium? The first thing you do is you reason. And you are going to say that you expect a pretty negative delta G because you know that the movement of sodium is favored by the membrane potential and it is favored by the concentration ratios that you have in the system. So you are going to expect a pretty big, or pretty negative delta G. So let's see if we get there. So for the concentration, we fill in the numbers here and we get to the negative 1.4 kilocalorie per mole. Right, so this is the point of origin, 150 over 15. That ratio is 10. The log of 10 is 1. So we get 1 times negative 1.4 is negative 1.4 kilocalorie per mole. And that tells us that indeed sodium is favored to move into the cell with these concentrations. Okay, and then for the membrane potential, we fill in the numbers here. And if we do it, then we take 75 millivolts or 0.075 volts, stick to the units, you get negative 1.7 kilocalorie per mole. Why is it negative? Because I'm reasoning actually that it should be a negative value. Because the membrane potential favors the inflow of a positive ion into a cell. So the only reason that this is negative is I say it has to be negative. So on exams you will say it has to be negative. Now, unless, of course, we have a chlorine ion that we want to move into the cell. Then it's actually not favored. Then we will get a positive delta G for the membrane potential, if that would be the case. Okay, so now we can just add these two up. We do that, and there you go, negative 3.1 kilocalories per mole. So the negative number tells us that the flow of sodium is indeed favored. It can drive something. We can say this system is like having some credit in the bank. It allows us to do something. It allows the cell to do work. How are we doing? What you should do is when you're at home, just go over these yourself. It's not hard. You can even follow. Okay, so now let's look at our sync-word system, where we have here the epithelium that lines the small intestine, and here's one of those epithelial cells, and it's doing the glucose uptake. Effectively, this cell mediates the transport of sodium and glucose over this membrane here, over the epithelial layer, right? And we know, you know because you did the exam, that there's one transport system missing here. That's the potassium channel here on this membrane is missing. But we're looking here at the top. So why is it 2 sodium for each glucose? Now we have to remember that the glucose concentration here in the cell is going to be pretty high. It's roughly 10,000-fold higher than the glucose concentration here in the lumen of the gut. So this transporter has to overcome a 10 to the 4th concentration ratio. And for a 10 to the 4th concentration ratio, to overcome that, we need a lot of energy. Actually 4 times plus 1.4 kilocalories per mole, which is 5.6 kilocalories per mole. Okay, so why is it 2 sodium? It's a matter of energy. To create that higher than 10 to the 4th concentration gradient, to accumulate the glucose in the cell to that high level, it takes this amount of energy, the 5.6 kilocalories per mole. Using one of the equations I just showed you. Calculate that. So We also calculated that if we take realistic values for membrane potential and realistic values for the concentrations of sodium, we have calculated that for each sodium we have a negative 3.1 kilocalories per mole that we get as credits to spend. So if we would have a coupled reaction of sodium, single sodium driving a single glucose into the cell, then the net energy there that we would be dealing with is the plus 5.6 kilocalorie per mole for the glucose and a negative 3.1 for the sodium, and that remains a positive value. And a positive value for the delta G tells you that the reaction will not take place. In fact, in that system, glucose goes out. So in order to drive the glucose in, you need to invest more. You need 2 sodium, which gives you 2 times the negative 3.1 in this example. That's negative 6.2 kilocalories per mole. That's the credit we have. That's the buying power we have in the system. And now for the total coupled reactions, if we add it all up, we have negative 6.2 from our sodium. And we need to spend plus 5.6 to get the glucose in to that high concentration. We end up with a negative net delta G, which means it's a favored reaction. It will occur in that direction. So, by coupling the reactions at the uniporter, the overall reaction is favored in this direction that we want.
If the total delta G was 0, would it not work?
You mean if the total here is 0?
Yeah.
Well, then actually what's going on is then the total reactions are at equilibrium, and then net flow is not happening anymore. Really, thanks for the question, it helps. So if we get a negative value here, that means that for our chosen direction, the coupled reactions will happen in that direction. If we get a positive value, it actually means that the reactions would occur in the reverse direction. If we get a 0, that means there's no net change. I hope that makes sense. Once again, I'm telling you, you should do this at home again. I think that helps to understand that better. Okay, now, so now we understand at least why it is 2 sodium and not 1. We can also understand why it's not 3 sodium, because that would be a waste of energy. It took a lot of energy at the sodium potassium pump to get that sodium out. So let's keep it out, let's keep the credit in the bank, if we don't need it. Now, it's nice to think about energy, but it's very difficult to measure energy. In fact, almost impossible to measure energy directly. Because energy really is the capacity to do work. And the capacity to do work is not easily quantified or measured directly. However, since we have delta G equals Z times Faraday constant times membrane potential times voltage, you can actually express everything in terms of a membrane potential by dividing by Z and the Faraday constant. So most of the time this means you divide by the Faraday constant and you get things in terms of a potential. So if we do that, then we actually see that the total energy, now in terms of a potential, the voltage, equals actually the existing membrane potential, taken out Z and Faraday constant, plus a term for the concentration, and here it is 60 millivolts times the log of the concentration ratio. And so this is true at 300 Kelvin again. So really we can say here, we can call this the motivation for an ion to move across the membrane, expressed in terms of something that we can measure, potential. So another word is the ion motive force. Some books use that. So we see there's 2 components to it. There's a membrane potential component and a concentration component. So really, you should understand that this formula is really the same as delta G total equals delta G volt plus delta G concentration. It's the same. Now there's a special case. And the special case is if we speak here about an ion gradient that involves protons. And it's a special case because it happens a lot and we have to deal with it a lot. In this case, we speak here not of the ion motive force, but proton motive force. And the unit is voltage, or volt. So, what we can say is that in terms of membrane potential units, volts, the motivation for a proton to move across a membrane, the energy involved there equals the pool of the membrane potential and another term which depends on the proton concentrations. And proton concentration ratios, and taking the log of that, then you get the change in pH. So the concentration term here is 60 millivolts times the change in pH. And this, what I have here in yellow and red, highlighted in yellow and written in red, is something you should know. You should understand what it means. The proton motive force equals the existing membrane potential and 60 millivolts times the delta pH. So what it means, if we have a membrane potential of say 60 millivolts and we have a pH of 6 and a pH of 7 in another compartment, and the ions want to move from pH 6 to pH 7, and the membrane potential works in the same direction, then we have 60 plus 60 times 1 is 120 millivolts. You can do it at home, you'll believe me. So once again, this is useful because we can measure potentials. Membrane potentials can be measured directly. Okay. So we've seen this system. You can imagine we have a cell, and we stick in a pipette, and in the pipette is an electrode. We have a reference electrode outside, so we can now measure the membrane potential over this cell here. Okay. So measure that. So now, if we have these sodium concentrations, and we're assuming now that we're opening a channel. So we're opening a channel so sodium can move down its concentration gradient. So we can now try to figure out what the membrane potential would be in that case. Okay. And to do that, you need a small derivatization of the ion motive force equation. And there's a biochemist called Nernst, believe it or not, this was a German. There he was. It was in Berlin at the same time that Einstein was there. And there were other people that were famous. And he came up with this equation. And here it is. And what it describes to us is the point where the membrane potential is such a magnitude that it counteracts the effect of concentration. Let's just go back. This system. So sodium would move in down concentration, right? Initially we say we have no membrane potential. But as soon as sodium moves in, there are charges that accumulate within this compartment. So it becomes positive in and negative out. So charges accumulate inside this compartment. It goes positive in and negative out. At some point, there's a membrane potential which is so big that sodium no longer wants to move in. The point where sodium movement stops, so the total delta G is 0, that point is where concentration and potential counteract each other in terms of magnitude. There's no net flow anymore. At that point, we call that the equilibrium potential, and it's given by the Nernst equation. And it's really just a derivative of what I've shown before. So that equilibrium potential, how do you get there? It's this equation. You don't remember that. But in simplified form and in our happy environment, we can say that the Nernst equation gives us 60 millivolts times the log of the concentration difference, or the concentration ratio, where in this case, CO, CI doesn't matter if you say in or out or intended or origin. You just have to reason for the magnitude of the sign, or for the sign whether it's positive out or negative out. Okay? So in the previous question, since we had a concentration ratio of 10, because we had 150 over 15, 150 over 15 is 10. Fill that in here, so we have the log of 10 times 60 millivolts, we get 60 millivolts. Okay, and it's going to be positive inside, negative outside, in that case. So that actually gives us sort of something that would be close to the action potential in a neuron during the phase when in a section of plasma membrane the sodium channels are temporarily open. Sodium flows in to the point where we reach the equilibrium potential for sodium. You would think if these are the concentrations, there would be something like 60 millivolts. So they'll probably be a little bit smaller than that. I'm not exactly sure. Yeah. Also, for the resting potential is really set mainly by potassium leak channels. And potassium is kept high in the cell by sodium potassium pump. It flows out through the leak channels up to the point where the membrane potential caused by that charge flow counteracts further outflow of potassium. And that gives the resting potential of roughly 70 to 90 millivolts. Okay. So potassium concentration gradient is a little bit bigger than 10. All right. So we, I